Hey students, this is a video on the root test. Now the root test is actually very similar to the ratio test, so make sure you've already watched my video on the ratio test. The only difference with the root test is it's still the limit as n goes to infinity, but instead of having the ratio of absolute value of a sub n plus 1 over a sub n, you actually have the nth root of the absolute value of a sub n. So instead of being a ratio, which is a fraction, you have a square root instead. Not a square root, actually an nth root. But it works a lot the same way as a square root does. And notice that because it's an nth root, if you have powers, that nth root can cancel out with the nth power, which makes it easy to simplify for certain types of problems. Now for the root test, like I say, the two cases are identical to the ratio test. So after you take the limit as n goes to infinity of nth root of absolute value of a sub n, if this equals L, or infinity, the series converges absolutely if L is less than 1, and it diverges if L is greater than 1, or if L is infinity. So notice that these two cases are exactly the same, or they're identical to the ratio test. So pretty much just the same thing. Okay, so let's go ahead and do some examples of this. But if you've already seen the ratio test, there isn't too much surprising here. Okay, so example, use the root test to determine whether the series converges or diverges. Okay, use the root test to determine whether the series converges or diverges. Okay, and for our first example, we're going to do a relatively easy one involving the root test. Okay, so for example number 1, we're going to go ahead and do, this is pretty similar to actually your fourth problem on your homework. So this one we have the sum from n equals 1 to infinity. The sum from n equals 1 to infinity of 5 over the quantity 3n plus 4, quantity to the nth power. Okay? Alright, and we want to use this new root test to determine whether the series converges or diverges. So again, the setup of this is pretty similar to the ratio test. It's called the root test though because we have an nth root instead of having a ratio. So we're going to find the limit as n goes to infinity of nth root of absolute value of a sub n. Okay, so limit as n goes to infinity of the nth root of absolute value of a sub n. Okay, so here that's going to be the limit as n goes to infinity of the nth root of absolute value of 5 over the quantity 3n plus 4, quantity to the nth power. Now, in most cases you don't need the absolute value, however sometimes you do need it. On this problem we don't actually need the absolute value, because on the top the absolute value of 5 is just 5, and then on the bottom, because n is going to positive infinity, this is never going to be negative. So 3n plus 4 to the nth power, that's never going to be negative, because n is going to positive infinity. So in this case we don't need the absolute value, so we can go ahead and just get rid of that. Okay, so if we get rid of the absolute value, then we just have the limit as n goes to infinity of, if we go ahead and distribute the nth root, we're going to have nth root of 5 on the top, And then on the bottom, we're going to have nth root of 3n plus 4 quantity to the nth power. Okay, so we have nth root of 5 all over nth root of 3n plus 4 quantity to the nth power. So on the bottom, the nth root and the nth power just cancel out. So we just get 3n plus 4 in the denominator. Okay, so really we just have the limit as n goes to infinity of nth root of 5 over 3n plus 4. Okay, and as usual, in this kind of situation, you want to actually divide the top and the bottom by the highest power in the denominator. Okay, so if we divide the top and the bottom by n, in other words, if we multiply the top and the bottom by 1 over n, that will get us where we need to go. Okay, just like we always do when we have a rational expression. Okay, so now in the numerator we're going to have nth root of 5 over n, and then in the denominator we're going to have 3 plus 4 over n. And we're still taking the limit as n goes to infinity. Okay, and then from here, because we're taking the limit as n goes to infinity, remember that nth root of 5 is the same as 5 to the 1 over n. So this is the same as 5 to the 1 over n. And 5 to the 1 over n actually grows a lot more slowly than the n in the denominator. So this here, the 5 to the 1 over n is actually going to 0. Because 5 to the 1 over n grows very slowly, but n grows much quicker. So because the denominator is growing much more quickly, this is going to go to 0. Okay? And then in the denominator, 4 over n is also going to go to 0. So after we do the limit, we just find that we have 0 over 3 plus 0, which is 3. And 0 divided by 3 is 0. Okay, and what this number is here that we found is L. So we just figured out what L is. And then for the rest of the problem, it's just like the ratio test. So when we look at our conclusion here, the two cases are identical to the ratio test. So if you watch my video on the ratio test, first case is if L is less than 1, it converges absolutely. And then if L is greater than 1, or if L is infinity, it diverges. Okay, so here, L equals 0. So since L equals 0, which is less than 1, that means that the series converges. And it actually converges absolutely. And notice once again with the root test, we did have an absolute value at the beginning. So it should kind of make sense in a way that the series converges absolutely. All right, and remember, if a series converges absolutely, it also converges. Okay, cool. So that was our first example of the root test. And then these problems can get more difficult, of course. It wouldn't be math if they were all super easy. Okay, so for example number 2, we're going to do the sum from n equals 1 to infinity. The sum from n equals 1 to infinity of 2 over the quantity 4 plus 1 over n, quantity to the 3n. Okay, so the sum from n equals 1 to infinity of 2 over parentheses 4 plus 1 over n, parentheses to the 3n. Okay, so fortunately in the directions they told us we're supposed to use the root test. So once again, we're going to be taking the limit as n goes to infinity of the nth root of this expression. So you have the limit as n goes to infinity of the nth root of 2 over the quantity 4 plus 1 over n, quantity to the 3n, and then don't forget you still have an absolute value. So you have an absolute value over everything inside of the radical. Okay, but just like with the last problem, we don't need the absolute value because we're taking the limit as n goes to positive infinity. So in the numerator, absolute value of 2 is just 2. And then in the denominator, this is always going to be positive. So we don't need an absolute value because it's already positive. Okay, so now we just have the limit as n goes to infinity of nth root of 2 in the numerator. And then in the denominator, we have nth root of the quantity 4 plus 1 over n, quantity of the 3n. Okay, and instead of writing 3n for our exponent, one thing we can do here is we can actually factor the n out and leave the cube on the inside. So that's what I'm going to do here. So instead of writing it down here as 4 plus 1 over n to the 3n, I'm going to go ahead and factor out the n. So I'm going to write it as 4 plus 1 over n cubed, and then I'll put brackets around it, and I'll factor out the n as the exponent. And you're allowed to do that because if you're raising an exponential to a power, you multiply the exponents. So this is the same as raising it to the 3n power. Alright, and then you're going to notice that the nth root and the n cancel out. Alright, so then everything simplifies. So now we have the limit as n goes to infinity of nth root of 2 over 4 plus 1 over n, quantity cubed. Alright, and then for the nth root of 2, what is that one going to go to? And how on earth do we do the rest of the problem? Well, I mean, we can plug in infinity down here, and 4 plus 1 over n quantity cubed, the 1 over n is actually going to go to 0. So that's the easy part. So let's look at that first. So the 1 over n goes to 0 because n is going to infinity. But then the question is, what does this nth root of 2 go to? Well, it turns out that you can actually use GeoGebra if you're wondering what the nth root of 2 looks like. You would actually go to GeoGebra, and then you would go, so you type in GeoGebra in your GeoGebra graphing calculator in your search engine, open it up. But because it doesn't have nth root, we're going to type in the xth root. So we do, instead of writing it as the xth root, I'm going to write it as a rational exponent. So I'm going to press the exponent button, and then, let's see, what do we have here? We have nth root of 2 would be the same as 2 to the 1 over n. Okay, so we have 2 to the 1 over n here. So the function I want to look at is 2 to the 1 over x, so we can see that. Okay, so what's 2 to the 1 over x going to look like? 2 is our base, then I press the exponent button, and then I type in 1 divided by x. And then we want to see what 2 to the 1 over x does as x goes to infinity. Because remember, as n goes to infinity, it ends up being the same thing as if x goes to infinity for 2 to the 1 over x. So as x goes to infinity here, we can see that our function is approaching 1 on the y-axis. See, on the y-axis this is 1, and the function is approaching 1 as a horizontal asymptote, which means the limit as x goes to infinity of 2 to the 1 over x equals 1. Alright, so in the numerator here, the limit as n goes to infinity of 2 to the 1 over n divided by, well, in our denominator we actually have 4 cubed. That's going to give us, well, this 2 to the 1 over n just goes to 1. So in our numerator we have 1, and then in our denominator we have 4 cubed. And 4 times 4 is 16, times 4 is 64. So we actually get 1 over 64 as our answer. Well, not as our answer, but that's our L. That's the limit. Okay? So this is L. And actually, since we looked up that limit here, there was another way we could have done the last problem, because you probably noticed that we had a similar expression in the numerator. So if I go back to the last problem, example number 1, way back here, when we divided 5 to the 1 over n by n, and I said that went to 0, one of the reasons that goes to 0, to write it out more specifically, is because the numerator here, the 5 to the 1 over n, the numerator is actually going to also be going to 1, just like on the problem that we were looking at. So the numerator goes to 1, but the denominator n goes to infinity. Well, 1 over infinity, with quotes around it, 1 over infinity equals 0. Okay, so that 5 to the 1 over n is just like 2 to the 1 over n. If you look at the graph of that one, the limit as n goes to infinity of 5 to the 1 over n is also going to be 1. So that one gave us 1 over infinity, which is still 0. Okay, so hopefully that makes sense. Alright. Okay, so anyway, going back to this problem, we got L equals 1 over 64. Okay, and once again, we have L equals 1 over 64, which is less than 1. So that means the series converges absolutely. Okay, the series converges absolutely. And with the ratio and the root test, whenever you get L is less than 1, that means the series converges absolutely. Both of those have an absolute value in them, so that should help you remember that they converge absolutely. But remember, if it converges absolutely, it also converges. So if you wanted to, you could just say the series converges, and that would also be true. Okay? So that was a good second example. Now for the third example, I wanted to do a harder problem that involves the root test. So for example number 3, we have the sum from n equals 1 to infinity of parentheses negative 1 to the nth power times parentheses 1 plus 1 over n parentheses raised to the n squared power. Okay. So this one is going to be trickier, but we can still do it. Okay? Okay, so this problem is tricky, but there's a little hint that they give us, which is really helpful. So, sorry, I dropped my pen. So the hint that they give us is at the beginning of the problem, they say hint, the limit as n goes to infinity, of the quantity 1 plus x over n, quantity to the nth power, equals e to the x. This is their hint. Okay? But they still want us to use the root test And at the end of the problem, we're going to see why we need this hint. Alright, but first off, we're just going to go ahead and use the root test. So we're going to apply the nth root to our a sub n here, and we're going to put an absolute value around it. Okay, and of course we're taking the limit as n goes to infinity. Okay, so we're doing the limit. Actually, let me move way down here. We're doing the limit as n goes to infinity of the nth root of absolute value of a sub n. So that's going to be absolute value of negative 1 to the n times 1 plus 1 over n quantity to the n squared times 1 plus 1 over n quantity to the n squared. Okay, and then of course that's an absolute value around that. So that's just the root test right there. Limit as n goes to infinity of nth root of absolute value of negative 1 to the n, parentheses 1 plus 1 over n, parentheses to the n squared. Okay, and then like I said, towards the end of the problem, we're actually going to use that hint that they gave us. Alright, so for starters, let's go ahead and talk about the absolute value. So the thing about the absolute value is this negative 1 to the nth power is going to be negative if n is odd, and it's going to be positive if n is even. So this one right here is going to be negative 1 if n is odd, and it's going to be positive 1 if n is even. Okay, but what this absolute value does is if it's negative 1, it makes sure it's positive 1, and if it's positive 1, it stays positive. So the absolute value is going to make it positive either way. And so what that means is we don't even need this negative 1 to the n. Okay, so because of the absolute value makes it positive. So it makes it 1 in either case. So it makes it positive 1 in either case, which basically just means that the absolute value cancels out with the negative 1 to the n. Okay, so this whole thing is just going to cross out with the absolute value. And then we don't need the absolute value anymore, because it just makes sure that that's always positive. And the rest of this, the 1 plus 1 over n to the n squared, that's always going to be positive because we're taking the limit as n goes to positive infinity. So we're going to be plugging in positive numbers there. Okay, so our absolute value just makes sure that it's always positive, so that cancels out with the negative 1 to the n. Alright, and then to finish this, we have to deal with this nth root of parentheses n squared. Remember that the nth root is the same as raising it to the power of 1 over n. So I'm going to go ahead and rewrite it that way. So we have the limit as n goes to infinity, limit as n goes to infinity of the quantity 1 plus 1 over n quantity to the n squared. Alright, and then we're raising this to the power of 1 over n. Okay, so brackets, raising it to the power of 1 over n. Because raising it to the power of 1 over n is the same as taking the nth root. And then remember here, if we use the rules of exponents, we can just multiply the exponents. So multiplying the exponents, we get limit as n goes to infinity of parentheses 1 plus 1 over n to the n squared times 1 over n. So the n squared and the n are going to cancel there. So we're just going to end up with an n in the numerator. Okay. And then this would be the point where most people would get stuck if they didn't have the hint. Because here we have the limit as n goes to infinity of 1 plus 1 over n quantity to the nth power. And because that's raised to the nth power, it's not really clear what this would become. But if we go back to our hint, with our hint that they gave us at the beginning, the limit as n goes to infinity of 1 plus x over n quantity to the nth power equals e to the x. And remember, this x can be anything. So this x right here can be any number. It could even just be 1. So that's what we have. We have the limit as n goes to infinity of parentheses 1 plus 1 over n to the n. So that's going to equal e to the 1. I hope you can see that. So here x is going to be 1 in this formula for the hint. So this is going to equal e to the 1. Okay. So here our x is 1. So we get e to the x, but here that's e to the 1. Okay, and of course any number to the 1 is the number. So our answer is e. Well, not our answer, but that's our L. Okay, so here L equals e. And remember, e is actually a number. It's not just a letter. And if you're not sure what it is, you can always type it into your calculator, but it's 2.7 something. So you go all clear, you press E, it's 2.71828. So L is approximately equal to 2.71828. It goes on forever, but we don't really care. But what's important about this one is, unlike the other problems we did, for this one our L is actually greater than 1. So remember, if L is greater than 1, if our L is greater than 1, that means the series diverges. Just the same way in the ratio test, if your L is greater than 1, your series diverges. And if you're doing your homework and you get your L is actually positive infinity, that would also mean that the series diverges. Okay, so if it's any number greater than 1, including infinity, the series diverges. Pretty cool, huh? And I guess that completes all the types of problems on your homework. So that's it for the root test. So thanks for watching. Have a good day.